Hello calculus fans, and welcome to section 8.2, where we talk about the area of a surface of revolution. The surface of revolution is formed when a curve is rotated about a line. Now section 8.2 is going to be a little bit of a continuation of section 8.1, where we dealt with arc length, because arc length is going to be part of the solution to this area of a surface of revolution. So what we'll do is I'm going to approach it from sort of a conceptual approach. So we'll start off with a region bounded by a couple of points A and B. And we've got this curve, y equals f of x right here. And we're going to rotate this about the x-axis. Okay, so we are going to rotate this around here. So we'll have something like this shape here. Then let's let ds be a small piece of the arc. Small piece of the arc from A to B along this curve. So ds will be this let's say this little point right here. This will be ds, just a little piece of this. Okay, so we'll have, just think of this as coming along here. And it's a little piece of this. And so of course it would be coming around the back side. So ds, this is the same sort of notation we used in 8.1, right? ds is like a little piece of the arc here, a little piece of the curve. So this is a little piece of that. And then we're going to rotate this small piece of arc around the axis of rotation, which is what we can see right here. And then think, if we were to peel this strip, so if we could somehow just like peel this strip off of here and flatten it. So if we did that, it would become rectangular, so it'd become a rectangle. So remember, this is a conceptual idea. So of course it's not going to be a perfect rectangle because it's curved, but we're going to eventually end up taking the limit of this, right? So when you take the limit, as this gets smaller and smaller and smaller and becomes more and more numerous along this edge here, it will become more and more like a rectangle, right? So just conceptually, just picture it as a rectangle. So the area of a rectangle, right? So basically, if we were to take that strip and lay it out, it would look something like this, right? It'd be a little rectangle here. That would be ds. This would be ds. And then this distance here would actually be the distance around here. So it's a circular distance, so it'd be 2 pi r, right? So the circumference of this thing is 2 pi r, which in this case, r is actually whatever that y coordinate is, right? So in this case, it'd be 2 pi y. All right, so back to the notes here for part 3. We've got a rectangle with area, which is, of course, length times width, which in our case would be 2 pi r ds, right? Length times width here. And so the area of the sample strip is going to be 2 pi r ds, but in our case, r is actually going to be the radius of this will be this distance here, which would be y, right? So we can look at this and see, okay, this radius here, this distance here, in this case, when we're spinning about the x-axis, that radius is actually going to be y. So the area of the sample strip in this case is going to be 2 pi y ds. So then to find the total surface area, what we're going to do is it'd be the sum of the areas of all these possible sample strips from A to B. And of course we can find that total by integrating over the function from A to B. So it's the same sort of idea as usual. We're going to break this up into a whole bunch of pieces and then find the area of each piece and integrate to get all of the pieces. Okay, so there's a couple of notes here. And this is just mentioning that the total surface area of the solid of revolution of radius r, formed by rotating the region about the x-axis, is given by 2 pi r ds. Now in this case, when we spun it about the x-axis, r was equal to y. But let's take a look at the note here. So the note is use 2 pi y ds when rotating about the x-axis. Okay, now you can imagine, just look at the picture and imagine if you spun it around here, if you spun it around the y-axis, well then the radius is going to end up being x, right? So the other note is going to say use 2 pi x ds when rotating about the y-axis. Okay, and then from previous work in section 8.1, we know what ds is, right? We have a formula for ds. So ds is 1 plus dy dx squared under the radical dx. Or the other version for ds is 1 plus dx dy squared under the radical dy. And if you remember, what we did is we used this one when y was a function of x, and we used this one when x was a function of y. Okay, so you have two different versions of ds, and it turns out we'll be able to use either one. So on the next page, we'll sort of put these pieces together for the formulas. So let's see if we can get this to cooperate. So we've got these 4 boxes to fill out. All right, and all 4 of these boxes are similar. But if you look at this first one, we're talking about the curve y equals f of x. So y is a function of f of x about the x-axis. Then we've got x is a function of y, still about the x-axis. So about the x-axis means we are going to use 2 pi y, right, for the x-axis. Now these other two, where these are the x-axis, these other two down here we're rotating about the y-axis. So these are going to be 2 pi x. Okay, and then also up here, this first box, this is the curve y equals f of x. So I'm going to set this one up like this. I'm going to say, so the surface area, a lot of times you use S for surface area, SA works, A works, whatever you want. But you see in a lot of calculus books, they'll use S for surface area. So we've got 2 pi. Now I'm going to pull that out in front of the radical, or in front of the integrand, the integral sign. So you got 2 pi. Now we know we've got a y here. So we've got y, and then we need ds, right? And ds is 1 plus dy dx squared dx. And I'm using this version of ds because we've got y as a function of x, so I'm just going to use this version. Now you can see that when we integrate here, we've got a dx problem, so we're going to have to change this y. But this is how we could set this one up. So y is a function of x. We're rotating about the x-axis, so it's going to be 2 pi y. Okay, so in this next case, we've got x as a function of y. So in this case, we'll probably use the other version of ds. So we could say s is equal to 2 pi. Still going to be y because we're spinning about the x-axis. But I'm going to use the other version of ds now because x is a function of y. So I'm going to write 1 plus dx dy squared, and then that would be a dy. Okay, so are you okay with this connection? Y is a function of x, so I use this version of ds with a dx. X is a function of y, so I use this version with a dy. Now we're going to see that these are interchangeable. You could use this version here and this version here. A lot of times it will matter though. One of them will be easier than the other. Sometimes one you won't be able to integrate exactly. You'd have to use an approximation. But usually it'll fall into place. Like typically when it's y is a function of x, just use this one. X is a function of y, you just use this one. Okay, so we'll see when we work on some of them. So that takes care of these two when we're spinning about the x-axis. Now these are pretty similar here about the y-axis. So it's going to be a 2 pi x. So the surface area here is going to be 2 pi. I'll put the x over here. And this one is y is a function of x. So I'm going to use the normal ds that we would use there, which would be 1 plus dy dx squared dx. Okay, and just I'm going to move this up a little just to make sure that the bottom will show up on the video. So this one is also 2 pi x, so we're going to go s equals 2 pi x. But now we've got the curve x as a function of y. So I'm going to use the other version of ds here and go 1 plus dx dy squared. That's a dy there. And dy. Okay, so those are like the sort of the methods that you can just go to that'll sort of fall into place. But if you look at the note below there, you can see that in each of the cases above, you can use either one of these formulas for ds. And as I mentioned, sometimes one will be easier than the other. Sometimes one we won't be able to really integrate, because these integrals, they can be a little tricky. Like if we're asked to integrate these by hand, like we often are with the Stewart book, and Stewart has to be real careful in these questions, because think about how to make this work. You take a derivative of a function, you square it, you add it to 1, it's under a radical, then there's other variable over here. So they have to be carefully chosen in order for us to be able to even do these by hand. Okay, but that's basically all the forms that you could have in this kind of problem. One thing I just noticed, you guys probably noticed and we're screaming at the screen, is I forgot to mention these the values for x or y, right? So in this case, these limits of integration here, x varies between a and b. So this would be between a and b. Now in the next case, y varies between c and d. So of course this would be c and d. And then we go back and we've got x again between a and b. So we need these limits of integration on here. I can't believe I forgot these, but I am getting old. Then over here, y varies between c and d. Okay. All right, so there, now everything is good. And now that you've seen the formulas, I know you are just like waiting so anxiously to try one out. So let's not keep you waiting. Let's try one of these out. Example 1 says, find the surface area of the solid formed by rotating this particular curve. X equals 1/3 y cubed, where y is between 0 and 1, about the y-axis. So first notice that it's about the y-axis. So that means what we're going to use is 2 pi x, right? Because it's going about the y-axis. So we can write our formula down here. So the surface area is going to be 2 pi, the integral x. And then because this one is x in terms of y, I'm going to use dx dy. So in other words, you've got x is equal to 1/3 y, 1/3 y cubed. So we need to find the derivative, right? dx dy. So I take the derivative and we're going to get 1/3 times 3, which is of course 1. So we get y squared. And then we have to square this, right? So in the formula, so we'll have dx dy squared, which would be y to the 4th. So I'm going to use this formula, 1 plus dx dy squared dy. And again, the reason I'm using dx dy instead of dy dx is just because this is the form this is given in, right? X equals 1/3 y cubed. If this had been y equals some function of x, I would have went dy dx and put dx here. Okay, so that's why I'm picking this. And remember, these are, you could do the other way around too. So if I really wanted to solve this for y and then take dy dx, I could use the other version of ds. But since this one's set up this way, I'm just going to use it this way. Okay, so then we've got, let's see, so this is going to give us, oh, also the limits of integration are 0 to 1, right? Y is between 0 and 1, so this is dy between 0 and 1. So this gives us 2 pi, 0 to 1, and, okay, we'll have 1 plus y to the 4th dy. So we're getting closer to an integral that we can start working on, but you might notice there's still a problem with this. This is a dy problem. We've got this x here. This is an easy fix though, because x is the same thing as 1/3 y cubed. So I can swap out this x with 1/3 y cubed. So the 1/3 I'm just going to pull out front. So that would give us 2/3 pi, 0 to 1, of y cubed times 1 plus y to the 4th dy. And this one turns out to be an easy integral, right? Because this is a u substitution problem. So we could do a u substitution over here. We could say, okay, so I'm going to let u equal 1 plus y to the 4th, and then du would be 4y cubed dy. So I've got a y cubed dy, so I need to get rid of this 4, right? So we could just go 1/4 du equals y cubed dy. And now I can swap these out. I can get rid of the y cubed dy and put in this place 1/4 du. So this would give us, let's say, I'm going to put the 1/4 out here. Then I have 2/3 pi. And then we're going to basically just have the square root of u du. Now we've got to work on these limits of integration, right? So this 0 and 1 were in terms of y. So, you know, we have a choice here. You can either use dummy limits and put all the originals back after you integrate, put all the y's back, the y values, or we can switch them out now. I'm just going to switch them out now, so by using this up here, right? So we'll use this. We're just going to basically say, okay, if y is 0, let's see what u is. So if y equals 0, u would equal 1 plus 0, so that would be a 1. And then we've got, what about if y is 1? So if y is 1, so I come up here. If y equals 1, u would be 1 plus 1 to the 4th, which is 2. We've got a 2 here. And now we can just integrate. So let's see, we've got 2 over 12 times pi, which is 1/6 pi, or pi over 6, right? Just cleaning up this here, pi over 6. And then we've got 1 to 2 u to the 1/2 du. So we can use the power rule here, and we'll get pi over 6 times this 1/2 plus 1 is 3/2, divided by 3/2 is like multiplying by 2/3. Then we go from 1 to 2. All right, so we can clean this up. This is really, let's see, 2 over 18, or 1 over 9, right? Oh, I forgot. Oh, I got the pi there too. So it's basically going to be pi over 9. This is pi over 9. And then we plug a 2 in here, and we get 2 to the 3/2. Plug a 1 in, we get 1 to the 3/2. So this is going to be 2 to the 3/2 minus 1 to the 3/2, which is just 1. And you can leave it like this if you'd like. Now, the way that Stuart will always do this, they're going to write it like this. pi to the 9th times 2 times the square root of 2 minus 1. And this is sort of a common power that you'll get in this section. You get numbers to the 3/2 power, and you'll see them written this way. So here's what they're doing. If you have 2 to the 3/2, okay, that's really equal to 2 to the 2/2 times 2 to the 1/2, right? Because here we would add these powers. So when you do this, if you can make this an integer, then you can just have like 2 to some integer power. So in this case, since it's 3/2, if we do it like this, we're going to get 2 to the 1, which is just 2, times 2 to the 1/2, which is the square root of 2. So that's where the 2 times the square root of 2 comes from. And this is pretty common. So you'll have answers that'll be like 17 to the 3/2. And when you look at the answer in the back of the book, they'll have 17 times the square root of 17. Same thing. So when you have something like this is fine like this or this, whichever way you prefer. But you'll see them like this in the answer key in the back most of the time. Okay, so there is example number 1. Hopefully that makes sense. And let's move on to the next one. Example 2. Okay, this time we're going to rotate about the x-axis. We've got this curve, y equals 2 times the square root of x. X is between 1 and 2, and we're going to rotate about the x-axis. So when they say x-axis, we're rotating about the x-axis, so that means we're going to have to use a 2 pi y, right? That just comes from the circumference of this circle. When you think about conceptually how we're doing this, with that circumference, the radius will be y when we're going about the x-axis. All right, so when you look at this one, we've got y as a function of x. So I'm going to just think of it as finding dy dx, right? I'm not really going to change this unless I have to. So let's just think of, so y is really equal to 2x to the 1/2. So then dy dx, where the power rule is going to be x to the 1/2 minus 1x to the minus 1/2, or 1 over x to the positive 1/2. And I'm just going to write it like this, because we're going to have to square this, right, to fit in the formula. So basically, let's write that formula. So the surface area is 2 pi. We know it's going to be y. Again, I'm picking either x or y just based on what we're rotating about. It's always the opposite. Rotating about the x-axis means the radius will be y, so it's 2 pi y. The other thing we have to pick is if we're going to use dy dx or dx dy, and I just go by whatever this is. If this is y in terms of x, I'm just going to find y prime, or in other words, dy dx, right? Then we've got 1 plus and dy dx. For the reasons that I just mentioned, because this is y in terms of x, so I'll go dy dx. And then this one would be dx. And then x is between 1 and 2, so it's a dx between 1 and 2, so I'm just going to go between 1 and 2. Now after this problem, we'll look at one where I'll show you if we switch this around, it'll still work. But I just go by what it's already set up as. This is y equals, so I'm going to go dy dx. If it said x equals something in terms of y, I go dx dy. So I just do it like how this is set up. And then this, again, is just always the opposite about the x-axis, 2 pi dy. Okay, so we get this set up. And we know dy dx. We have to square it, though. So I'm going to do this over here also. Dy dx squared is 1 over the square root of x squared. And that's just going to be 1 over x. So this means the surface area is 2 pi, 1 to 2, y, and this will be 1 plus 1 over x dx. So we get here, we notice this is a dx problem, so we have to deal with this y. But once again, we have an easy solution because y is just 2 times the square root of x. So I'm going to get rid of the y, and I'm going to put in its place 2 times the square root of x. Now this 2, I'm just going to bring out front and multiply it by this 2. So that would just give us 4 pi, right? I'm multiplying the 2 pi by 2. And over here we'll have the square root of x times 1 plus 1 over x dx from 1 to 2. And now we have to think about how can we integrate this function. Well, this is definitely not any integral, a common integral that we would have like on a sheet of integrals, right? And it definitely doesn't look like u substitution or anything like that would work. But we do have a radical times a radical. We know from, algebra class, if we have the square root of a times the square root of b, that is the same as a square root of a times b, right? It works when you multiply. Not when you add, though, right? Although sometimes students do try to convince me of this. They try to convince me this is true all the time. Not you, not who's listening to this, but it's those other students. They try to convince me of that. But that is definitely wrong. It only works when you multiply, right? Okay, I don't even want to write that on there. It looks very bad. Only works when you multiply or divide. Then you can do things like this, when you multiply or divide. Okay, so we can do that here. So we could just multiply this through. So really, I just to save a little space, I'll do it right here. This is the same as x times 1 plus 1 over x, all under this one radical. And that means I can distribute this through. So if you distribute it through, then we'd get x plus 1. Right? So really what we've got is 4 pi from 1 to 2 x plus 1 dx. And this looks a lot nicer than this, right? But you can see it. This is the same, right? If I distribute, I get x times 1, which is x times 1 over x, which is 1. And then from here, we can definitely integrate this one because we can do a u substitution here. We could say u equals x plus 1, du equals 1 dx or dx. So then basically we're just going to have 4 pi. The square root of u, which I'm just going to write as u to the 1/2, du, right? Because this is u, so we've got the square root of u, which is u to the 1/2. We have to deal with these limits of integration, though. So let's come back over here and consider that. So this is a dx problem, so x goes from 1 to 2. Now we have a u, du problem, so we have to figure out what u goes from. So it's pretty easy. We just go back over here and we say, okay, if x equals 1, right, if x equals 1, then u equals 1 plus 1, which is, so if x equals 1, I plug a 1 in here and I get u equals 1 plus 1, so u equals 2. Okay, so that's going to be a 2 here. Then also if x equals 2, then u would be 2 plus 1, so u would be 3. So plug a 3 here. Okay, then we just integrate like we normally would. We've got the power rule. 1/2 plus 1 is 3/2. Divided by 3/2 like multiplying by 2/3. So we have 4 pi times 2/3 u to the 3/2 from 2 to 3. Remember also, once we change these limits of integration, we never go back, right? We're not going to go back to x. The only time we have to go back to x is if we use temporary dummy limits, right? Once we change these limits, we have an equivalent problem. This and this, these are equivalent problems. They look different, but they give the same answer. So once we change these limits, there's no need to go back to x. So then right here, basically this is what, 8/3 pi, and then we can plug in 3 and then 2. So we really have 8/3 pi, then we have 3 to the 3/2 minus 2 to the 3/2, which of course you can leave it like that, but what you'll see in the back of the book will be, the answer in the back would be something like 3 times the square root of 3 minus 2 times the square root of 2. For the same reason we talked about in the other problem. When you raise something to the 3/2 power, this is equivalent. Okay, so hopefully these are making sense. 8.1 and 8.2 are kind of similar in that the integrals sometimes look a little strange. We just have to algebraically manipulate them so that they look less strange, right? They start to look familiar. And I just wanted to try one of them. This is in the book. It's number 7 in the 8th edition, number 9 in the 9th edition. So let me write this one down. I just want to try it a couple different ways. So the problem is this. All right, so as I said, number 7 in the 8th edition, number 9 in the 9th edition, but here is the problem. We have the graph y equals x cubed. X is between 0 and 2. We want to rotate this about the x-axis. And we want to see what the surface area is, of course. Okay. So just looking at the problem, I'm going to just notice a couple things. I'm going to do this two ways. I'm going to do it more the natural way, then I'm going to show you that it works the other way too. So about the x-axis means we have a 2 pi y problem, right? The radius would be y. And since it's y in terms of x, I'm just going to find dy dx. So dy dx is 3x squared. So if we square dy dx, we get 3x squared, which would be 9x to the 4th, right? So we set up our formula. So the surface area is equal to 2 pi y, 1 plus dy dx squared dx, and x goes between 0 and 2. So this gives us 2 pi 0 to 2y times 1 plus 9x to the 4th dx. Okay, so we have the usual problem. We have a dx problem. We've got this y here we have to get rid of. But there's an easy solution because y is exactly the same as x cubed. So I'm going to get rid of this, put an x cubed in its place, which is quite convenient if you like to do u substitution. Because then we can see that if I let this be u, there's a multiple of the derivative right here, right? So let's do that u substitution. Let's go u equals 1 plus 9x to the 4th. So du is going to be 36x cubed dx. What we've got is x cubed dx. But we can fix that. We could go, okay, so 1 over 36 du equals x cubed dx. And then we've got just what we need. So we will swap this out with 1 over 36 du. But we've got to deal with these limits of integration. You know, a lot of review of u substitution in this section. So over here, we're saying, okay, x goes from 0 to 2. So what does u do, right? So we could say, okay, if x equals 0, then u is going to be 1, right? Because if x equals 0, put a 0 in here, u equals 1. That one's easy enough. If x equals 2, u equals. If I plug a 2 in here, I get 2 to the 4th, which is 16, right? So I get 9 times 16, which is 144, plus 1 gives us 145. Okay, a little unusual, but that's just what we're going to have for our limit. Okay, so then we can say this is equal to, so we have 2 pi times 1 over 36. Our new limits are going to be 1 to 145. And we basically have the square root of u du. So the square root of u I'm going to just write like this. Right, because u is 1 plus 9x to the 4th. We have the square root of u, which is u to the 1/2. And now we're ready to integrate. So we can use the power rule here. This goes up 1 to 3/2, divided by 3/2, which is like multiplied by 2/3. So we get 2 pi times 1 over 36 times 2/3 u to the 3/2, and then this goes from 1 to 145. Of course, we can clean all of this up, right? So this is what, 4 in the top, which will cancel that 36, become 9 times 3. So for that, we're going to get, that's going to be, what, pi over 27, right? Pi over 27 by the time you clean up all of this. And then we have u to the 3/2, and I plug in 145, so I'm going to get 145 to the 3/2 minus 1 to the 3/2. Or another way of writing this would be pi over 27, 145 times the square root of 145 minus 1. Okay, so that's probably the way you would do this. But if you really wanted to use the other version of ds, okay, so remember, when we set this up, this problem, we used this version of ds. We used 1 plus dy dx squared dx. But we could, if we wanted to, we could use 1 plus dx dy squared dy. So just to show you that it works either way, although it's going to be much easier this way, but I'm just going to show you we could set it up another way. Okay, so let's do the same problem. Okay, so same problem, we just do it again. We've got y equals x cubed, and x is between 0 and 2. We're going to rotate about the x-axis. Okay, so about the x-axis still means we're going to use 2 pi dy, or 2 pi y. The radius will be y, same as before. But this time, if we're going to do this, I'm going to have to, if we want to use the dx dy, I need to solve this for x. Which we could do. I could just take the cubed root of each side, right? If I take the cubed root of each side, I get y to the 1/3 equals x, just taking the cubed root of each side. So you get x equals y to the 1/3. So then dx dy will be 1/3 y to the negative 2/3, right? Which is like 1 over 3 y to the 2/3. Then I need to square that. So we need to do dx dy squared. Okay, I'm going to write it so maybe it'll be a little easier. Maybe it won't be. All right, let me just write it like this. 3y to the 2/3 squared. Okay, so when we square this, we can square the 1 and we get 1, and then we square this. We square both of these. So 3 squared is 9. Y to the 2/3 squared looks like this, where we multiply these numbers, so we get y to the 4/3, right? So when we square this, we're going to get 1 over 9y to the 4/3. All right, so when we put in our formula here, let me make a little room for us here. So we put our formula in, so we're going to get surface area equals 2 pi y. Now we're going to, because we're using this other form of ds, we're using 1 plus dx dy squared dy. Since we're using this form, well, we're also going to have to find our limits for y. So x goes from 0 to 2, and y is x cubed, right? Y is always going to be x cubed, so when x is 0, y is 0. So I put a 0 for my lower limit. For the upper limit, when x is 2, y is 2 cubed, so y would be 8. So the upper limit is 8. So what we're going to get is 2 pi, 0 to 8, y. Then you go 1 plus 9, oh, not 9. 1 plus 1 over 9 y to the 4/3 dy. So this one is significantly more difficult to solve than the other one. So I'm not going to go through this one. This one, I guess what you would try to do is maybe get the common denominator here, combine these. This one's going to be rough. This is going to be rough. I can tell you, just if you want to verify, if you go to, like whenever you have an integral and you're online and you want to just quick check things, a good spot is wolframalpha.com. And this actually does more than just math. It's kind of an interesting site. But wolframalpha.com allows you to just plug in integrals like this. And if you plug this in, it will tell you exactly what we got on the first one. So it's going to, it'll tell you the same thing that we got. It's going to say pi over 27 times 145 times the square root of 145 minus 1. So this is just kind of set up so you can use either version of ds, but one is typically much easier. And usually it's just the one that comes naturally, right? When we did this the first time, they gave us y equals x cubed, so it's more natural to just find dy dx. But if you really wanted to do it the other way, or something comes up where the first way isn't working, you can always pick a different version of ds. And it changes, right? The first one was a dx problem. This is a dy problem. All right, so it isn't like a big thing. You normally, however you initially do it is the way it will work, but this is just showing that it does work the other way also. Okay, so that should take care of 8.2. So go ahead and give it a try. There's some algebra involved to manipulate the integrals, sort of like 8.1, but some of these are actually a little easier because U substitution comes up a little easier because of this fact that we have this 2 pi x or y. So sometimes these are a little easier. But give them a try, and when you have any questions, let me know, and I'll talk to you soon.